Hello, calculus fans! Today, we are going to be proving one of Euler's most important contributions to mathematics, Euler's formula. Essentially, Euler's formula establishes the relationship between two groups of functions, the trig functions and the complex exponents. In the easiest to understand notation, this is the function. Before we begin our proof, we need some background information. First, remember that I represents the imaginary numbers. The exponents of I can be expressed in a pattern. Basically, the exponents of I repeat in a cycle of 4. So I to the power of 0 equals 1, I to the power of 1 equals I to the power of 2 equals negative 1, I to the power of 3 equals negative I, and on and on and on this repeats in a cycle of 4. Next, we need to remember some basic Taylor representations. Out of the 4 basic Taylor series we learned this year, we need to know sine of x, cosine of x, and e to the power of x for this proof. In case you forgot, the Taylor series for sine of x, cosine of x, and e to the power of x are shown on the board. Now, we are finally ready to begin our proof. We will do this by manipulating the right side of our formula to match the left side. Our first step is very simple. All we do is direct substitution. We substitute in the Taylor series for cosine of x and sine of x into our formula. Next, we distribute the I to the Taylor representation of sine of x, and then rearrange the terms based on increasing exponential values. Basically, we're working with the highlighted red portion of the formula. After doing that, we get 1 plus I times x minus x squared divided by 2 factorial minus I times x to the power of 3 divided by 3 factorial plus x to the power of 4 divided by 4 factorial, and so on. At first, this seems like it has no pattern. However, using our basic knowledge of I and the fact that its powers exhibit a cycle of 4, we can substitute in various exponents of I in order to create a visible pattern for ourselves to see. How this replacement with I works is very easy to see with examples. For example, the subtracting of a real number can be replaced by I to the power of 2 as highlighted by the red, while the addition of a real number can be substituted by I to the power of 4 as shown by the blue. Next, we rearrange the terms in our equation again. Basically, we just combine the I and x values that have the same exponents. The final step in our proof is to simply recognize that our equation now looks very similar to the Taylor representation of e to the power of x. The only difference is that x is instead I times x. Congrats! You now know a simple proof to Euler's formula, and you can use this to derive many things. But now let's learn why this formula is so significant. Euler's formula is basically everywhere in math, physics, and engineering, but most of it is above our level of understanding. For example, it can be used in mechanics to represent the angle of rotation, or in electrical engineering to represent signals that vary periodically. In addition, Euler's formula is useful in defining other functions of complex numbers because it can be graphed as a unit complex circle. Finally, Euler's formula evaluated as a specific case where x equals pi has been called the most beautiful theorem and the greatest equation because it contains the 5 fundamental constants in mathematics.
created using Powtoon.